This lesson is going to make an introduction into solving equations numerically, of which there are many different techniques, and we'll look at some of those. My question to you that I want you to think about is what equations are possible to solve in a nice way? Like you're going to get an exact answer, you know the method for it to work. What kind of equations, and then what equations are not possible to solve in a nice way? So pause the video and have a think. So some of the first equations you kind of solve potentially are things like x plus 2 equals 11 and 2x equals 8. And these give nice whole numbers. You can change it to make it like uh, maybe 3x equals 8. You can then start doing things like adding an x to the other side. And essentially, we learn how to solve linear equations with x's on both sides. Ax plus b equals cx plus d. And when you first learn about these, potentially, they're quite difficult. But at this point, you have learned how to rearrange and make x the subject of equations like this. You then tend to learn about quadratics. I mean, a and b and c and d could even be fractions here, so we can make it a bit more tricky. But we learn quadratics, and we learn about the quadratic formula, and about how that doesn't come from thin air. It comes from completing the square and deriving it. We learn how to solve sine x equal to a constant. I was about to write 7, but that doesn't make any sense. 0.7. And then even exponentials, e to the x equals 4, even log equations, and then learn equations. Learn of x equals 6 or something like that. And this is quite a lot of the equations that we sort of learn up to A level. The thing is, there's a lot of other equations, and they're not so easy to solve. And actually, some of them come from just even combining some of these things. So x plus e to the x equals 0. Suddenly, this becomes much more difficult because the thing is, when we had e to the x, we could take ln of both sides to get x by itself. When we had ln x, we could undo the logs. But here, when you start trying to undo like e to the x, you're going to end up, it's just not going to work out. The methods you have are going to fail because suddenly you're finding ln of x. Actually, you don't want to do ln of both sides because that would be ln of 0. But if you write it as e to the x equals minus x, then finding ln of that will not be easy because you'll get x equals ln of minus x. And how do you kind of figure out what that will give? Basically, most equations you see in maths, if you were just to write them down randomly, will not have exact nice solutions. Sine x equals e to the x. How many solutions will that have? And even things like cubics. So when you start writing cubics down, they in general they won't factorize. They'll be quite horrible. Now you might say, hey, there is a closed form solution for all cubics. I can write it in terms of square roots and cube roots and the like, and that is true. So maybe that's not the best example, but basically this equation becomes much more difficult to solve as soon as I start putting a cube in. Now I might have x to the 5 in there as well. I might even then have x to the 5 and then start adding a sine x. And these equations will quite often, will generally have solutions, but being able to find them is where we're not so easy, and that's where numerical methods really come in. What we say essentially is that these nice equations on the left, we can use analytic methods, logical reasoning, taking logs, undoing logs. However, these equations on the right require numerical methods that are approximate. We're not going to get an exact solution. We're not going to be able to write our answer as ln 4, which is that really an exact thing anyway if you don't really know what ln is? But I guess it's defined as the function of something at least, whereas here you're going to get like 1.234. Oh, I've rounded that to 4 significant figures, but actually it's going to go on forever potentially. So this is the kind of thing we're going to look at in this section. Okay, moving on then, back to cubics. Okay, so let's say There's no simple analytical method of finding the solution to this cubic. It doesn't factorize. There is a way of doing it. You can investigate, but it's not a very nice way. And I could do an example where it was even more horrible, but I'm trying to make one that you're familiar with. So you can plot this graph, and one thing you may have done before is do numerical methods, numerical solutions from the graph. So where is this graph equal to 0? Well, it's going to be here, which is about 2.4. It's going to be here, which looks about not minus, 0.5, and here, which looks to be about minus 2.8. There, give or take. But we don't, these are only rough. And actually, we're going to take it a little step back. We're going to do something a bit more simple. And that is to say, you can see from the graph, actually, that the roots of the equations lie in these intervals between minus 3 and 2, between 0 and 1, and 2 and 3, because, we're just sort of looking at little blocks of integers of where it lies between. And that's actually part of what we're going to do today, because we want to kind of look at what's going on these little blocks. And if we think about the function, let's think about over here. What's going on with the function at minus 3? Well, it's negative, and then it becomes 0, and then at 2 it becomes positive. So what I'm saying is it was negative, it goes through 0, and it becomes positive. I'm not going to say any more on that at the moment. For this one, it's positive, then it becomes 0, and then it becomes negative. It's like the opposite sort of thing. And then here, it's negative again, and positive, 0, and then positive. And I suppose that had to happen. We had to, if we're going from negative here, we're going to have this sort of link in with the signs. But basically, the thing I'm trying to get across is that there's been a change of signs finding the solution. If I look to the left and to the right of it somewhere, there's one place it's positive, and then the other it's negative. Somewhere through it, there's been a change of signs, and that actually is our main idea of the topic today, the sign change rule. And we can use this idea essentially to find roots, because I've shown you a graph and said, look, hey, here it's 0, and here it's negative and positive, but we can do the opposite, and that is to say, if we see here we go, I'm jumping to it now. The sign change rule says that if the function is continuous, we'll come back to that, for an interval a to b, and f of a and f of b have opposite signs, i.e. one's negative and the other's positive, or vice versa, then it must be that in between there is at least one root, that is where f of x is equal to 0. So what I'm saying is if I've got my graph and here it's negative, here it's positive, and I know it's continuous, so it's not going to jump. There must be somewhere in between where it's 0, and that is the sign change rule. And it's not particularly difficult, I don't think, to understand that, but it's quite powerful at trying to find solutions to things. So when a graph passes through the x-axis, it either goes from being positive to negative or negative to positive, and we can use a sign change rule to find these roots out. There's a few things we need to be careful of, however, and these are the things I've essentially highlighted in green. Okay, so basically, there's at least one root. Well, actually, there might be more than one root. If I look at this left-hand graph, then at A, we've got a positive function, and at B, we've got a negative function. But actually, I've got multiple changes in signs. That can happen with the sign change rule. It's just telling you that there's at least one root in between the interval. Something of note is if there isn't a sign change, like here the function's negative and here it's negative, it doesn't mean there isn't a root. So if you find a sign change, there is a root, but if you don't find a sign change, you still don't actually know, because it could be that there are an even number of roots, like we've got here. So I suppose, this is nicely said, if you get a sign change, you're going to have an odd number of roots, 1, 3, 5, 7. If you don't have a sign change, you're going to get an even number of roots, 2, 4, 6, or 0, of course. There may be no roots, if I was to look between here and here, for example. And the last little point to make is about this continuity. You can get a sign change, but is no root if you get a discontinuous function like the one shown. So here I see it's positive, here it's negative, but actually it's jumped from positive like infinity as such to negative infinity through this asymptote, and there isn't actually a sign change. So something to be aware of. Sign change only implies a root, or at least one root, if it's a continuous function in the interval. Of course, you might get, this is a weird thing, you might get discontinuous functions that are continuous over certain ranges. That's possible. If this function then, carried on like this, for example, then it's okay. So it's really important that it's in the interval. It's continuous in the interval. If it's discontinuous in the interval, then you can't assume and use the sign change rule. Let's look at some examples. As always, my recommendation is that you give this a go and then see if my solution agrees with yours. Okay, so we've got a curve y equals f of x. How does the graph show that f of x has a root between 2 and 3? Well, this is really just testing us on what a root is, and the fact is that the graph crosses the axis between these points, and that's what a root is. So the graph crosses the x-axis between 2 and 3. So there is a root between these values. Haven't really used the sign change rule here, just like sort of explained what a root is. Okay, the sign change rule is going to come in for part B. So show that f of x has a root between x equals 1.4 and x equals 1.5. Less obvious from the graph. Let's find out what f of 1.4 is. To be honest, for this sort of question, because it's quite technical, it might be best to use the table function and then type in the function x cubed. Of course, you can just find the values. Minus 4 x squared plus 3 x plus, whoops, what happened there? Okay, and then I'm going to start at 1.4, end at 1.5, go up in steps of 0.1, and it will find both values for me straight away. So 0.104 and f of 1.5 is minus 0.125. Okay, we've done the key bit, but actually we need to write a conclusion now. And this is what I would write word for word. I would say there is a sign change and I'm just going to say that key thing, f of x is continuous. I'm even going to write on the interval. So f of x has a root. Between 1.4 and 1.5. Actually, it has at least one root, but the questions just said show it has a root. I would recommend that. I would recommend saying that it's continuous just to, just do a little check in your head when you're doing this sort of question. Yes, it's continuous. And we've shown there's a sign change with this little bit. and so that's comprehensive. Okay, next question. Have a go again and then unpause the video when you want me to go through it. So part A, I'm going to just do a little sketch. It doesn't have to be perfect, but I'm going to sketch y equals ln x. Now we need to remember what this looks like. I'm going to do it in red. Okay, that's basically what ln x looks like. Actually, I've just made it look like it goes back down. Okay, I'm going to label that. And then in green, 1 over x. Explain how the diagram shows there's only one root. Ln x equals 1 over x only has one solution. I'm pointing to where that is. So f of x equals ln x minus 1 over x, because that's essentially the same thing, because it's when this thing is equal to 0, only has one root. Done. Show that this root lies in the interval 1.7 to 1.8. This is going to be very similar to last time. F of 1.7. Okay, this time I think it's not that, I'm going to do the alternative way of doing it. Good old, just put it in. It's going to be ln 1.7 minus 1 over 1.7. That's equal to minus 0.057. And if I do the same with 1.8, 0.0322. So again, I've shown that one's negative, one's positive. I'm going to basically do a carbon copy conclusion. There's a sign change and f of x is continuous on the interval, so f of x has a root between it, but this time I'll say in the interval 1.7 to 1.8. Okay, so get into that habit, show there's a sign change, and then write this sort of conclusion down. I would advise you talk about continuity, because actually 1 over x, this function is not continuous everywhere, because it's got 1 over x in it, so it's not defined at 0, for example. It's just a more awkward function, but it is absolutely fine in the interval. Okay, I'm going to just delete this now so I've got space to write. Whoops. Right, part C, given the root of the function is alpha, show that alpha equals 1.763 correct to 3 decimal places. This is a slightly technical question now. How do we show that it's correct to 3 decimal places? Well, sometimes I see people just trying to make it like checking 1.7639 and 1.763, what, not 1.7629 and 1.7631 and things like that. Basically, we've written this number down to 3 significant figures, and I'm going to write the next number that it would be, 1.764, and then 1.762, and we just have to show that it's closer to 1.763 than to 1.762. Now it's not, it's not necessarily just because it's really, you might work out what 1.762 is and it's like quite far apart, like it's quite far away. That doesn't mean that actually the root's nearer, because maybe it does, I don't know, maybe it comes up a bit like this and then goes like that. So this particular function, although the value of the function is, well, it's more negative, like it's got a larger magnitude at 1.762. It's actually, you can see the root is closer to it. So I'm just trying to give an example. You shouldn't just compare values of 1.762 and 1.763. The key thing to do really is as follows. Consider, like, there's nothing wrong with how I've set it up. Actually, what we want to do is look at the halfway points between them. Look at 1.7625 and 1.7635. And if I can show there's a sign change between these two, then I know the root lies between in this range here, and therefore, if I was rounding it to three significant figures, it's going to be closest to this one because it's somewhere along here. Okay, that's the trick to this kind of question. Quite commonly asked, actually. So, it's going to be very similar sort of thing, but I'm going to find f of 1.762 5. Okay, and it's minus 6.426. But it was in standard form, times 10 to the minus 4. It's very, very small here, but still non-zero. 1.7635. There we go, it's positive, 2.463. So how does this show it? Because we've basically done what I said. We've shown that there's a change in sign in this interval here, and so if I'm rounding it, it's going to round to 1.763. To be honest, I think this time I don't really need to talk about it being continuous and the like. I can simply say, what is it? I'm just going to need to check that. Alpha equals 1.763 to 3 decimal places. Hopefully I've convinced you, and that is a convincing argument. Okay, very last little bit. I'm going to make a little confession actually. This is non-examinable on the current specification of A-level, but I think it's worth having a go at. I'm not going to give loads of questions on it, but actually when you think about it, we've not really created a method for how to solve equations numerically and get accuracy. All we've done is look at the sign change rule and see, oh yeah, because there's a sign change, there must be a solution between this interval, and they've given us the answer here, and we've just kind of shown that it's the case. But how do we actually get an answer to an appropriate degree of accuracy? If I said I want the answer to 5 decimal places, how would you construct a method for obtaining that? Well, in the next two lessons, we're going to find really efficient ways of doing that. They do have their downfalls, which will be discussed. But this is like the kind of simplest to understand method, and it's called a decimal search. So I started off by saying I've got e to the x equals minus x. It has a solution between x equals minus 1 and x equals 0. Use a decimal search to find this root correct to 3 decimal places. I might have accidentally, probably shouldn't have used the word root here, because technically I'm finding the root. So I might let f of x equal e to the x plus x. And actually, sorry, I'm finding the root of this equation. Because a root is where it crosses the axis. Do you know what? I sometimes still get confused. What does root actually mean? Is it the solution to an equation, or is it where the graph crosses the axis? I think it's the latter, but in any case. Right, so let's find the root. Well, how am I going to do this? Well, what I can do, and it's, it's not that technical. It is simply the decimal bit comes in. I'm going to investigate different values of x, 0, 0.1, and this is the decimal part. I'm basically going to split it into 10 because I've got my little range, and I've probably realized I'm not going to be able to fit this onto my screen, but I'm going to do it on my calculator, so I'm going to use the table function. F of x is now e to the x plus x. I'm going to start at 0. No, wait a minute. It would start at -1, sorry. End at 0. I'm going to do steps of 0.1, and this is the beginning of my decimal search. I can see it's negative, and then it changes at -0.6 and -0.5. I don't know why I even did that. Like to do it in full, I should write everything down, but it's just going to take a long time, so I'm not going to bother. I'm going to write -0.6, -0.5, and I'm going to write the value of f of x for that one. And I'm happy if you do a question on this that you do the same. So -0.051 and 0.1065. Okay, so I know that the solution is going to be between these two values. But I'm trying to find it to 3 decimal places. So what does the decimal search do? It now uses -0.6 as a starting point and -0.5 as the end point. And I'm going to split this into 10. So I'm going to get -0.59, -0.58, and so on. I think I have to do the whole thing again. E to the x plus, it's arduous, but it is a method that can help me find a degree of accuracy as much as I want. So obviously you have to get the interval to start with, and if I didn't give you this, you might plot a sketch and see roughly where it would be. I might show you that in a minute. Otherwise you just have to try some numbers out. So actually the starting number I've not really talked about today. So we're going to start at -0.6, end at -0.5, step this time of 0.01, and there we go. We can see it's between -0.57 and -0.56. I've got 0.0112. Do you know what? It's probably easiest if I just do a little screen grab. Okay, so I can now see that my solution is going to be between these two values. I'm narrowing it down using this decimal search. I wanted to correct to 3 decimal places. Do you know what? I think I'm going to change the question. No, you got the idea now. There's just no need to carry on. 2 decimal places. I suppose the question is it nearer to minus 0.57 or minus 0.56? And I think that's just where the final bit's going to come in. Well, let's look at the middle point of that. So I've got the function is it's negative here, it's positive here. Let's find out what f of minus 0.565 is. And I think I'll do away with the table function. E to the minus 0.565 plus 0.565. I think I've made a mistake. Sorry, because it's e to the x, that should have been minus. Okay, there we go, 3.3601 times 10 to the minus 3. So it's also positive, and therefore it's going to be in this region, it's actually going to be 0.057. Root is minus 0.57 to 2 decimal places. I'm glad I didn't do 3. It would just been the same sort of process carrying on. So there we have it. There's the sign change rule, and here is how you can implement it. Oh, some of my graphics have disappeared, but here's how you can implement it using a decimal search to narrow it down. We will look at more sophisticated methods in upcoming lessons.